NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new. More mysterious, more beautiful than humanity's dream.
The edge of the known cosmos has just revealed something odd. It's so odd, in fact, that a scientist who won a Nobel Prize is speaking out. More than just a beautiful image has been taken by the James Webb Orbit Telescope, humanity's most potent eye in orbit. It discovered something that shouldn't have been there and doesn't quite fit. How can this finding change how we think about the origins of the universe? Could it indicate a missing chapter in the history of the universe? Or is it an indication that we have always had the wrong perspective on the universe? The farther we look, the farther back in time we travel, and what we just saw may not be from the history we anticipated, so fasten your seatbelt. The cosmos as seen by Jube. With a mission designed especially to investigate the early universe, the James Webb Space Telescope, or JWST, is the most potent and sophisticated observatory that humanity has yet launched. JWST is designed to observe infrared light, in contrast to its predecessor, the Hubble Space Telescope, which primarily recorded visible and ultraviolet light. This is important because light from old galaxies stretches into longer, redder wavelengths as the universe expands, a process called redshift. JWST can observe celestial objects that formed only a few 100 million years after the Big Bang, a time period commonly referred to as the cosmic dawn, thanks to infrared detection, which enables it to look considerably further into the past. The key components of JWST's capability are its larger 6.5-meter segmented mirror and its operational altitude beyond Earth's heating and light interference at L2. The telescope's multi-layered sunshield keeps the equipment extremely cold and enables them to pick up faint infrared signals from galaxies that are the furthest away. The Deep Field image, which revealed hundreds of galaxies in previously empty space, is among the first accomplishments under JWST. Many of these galaxies appear to be much older and more developed than would be expected at such early dates based on traditional cosmological models. A thorough spectroscopic examination was made possible by JWST's NIR-CAM, near-infrared camera, NIR-SPEC, near-infrared spectrograph, and MIRI, mid-infrared instrument. With the aid of these tools, astronomers may not only document the splendor of far-off galaxies, but also analyze light to reveal the chemistries, star formation rates, and velocities of the galaxy. For instance, there are real questions raised by the discovery of galaxies like Jade, GS, and Yezithasaro that were believed to have formed only 320 million years after the Big Bang. In a young cosmos, how can such massive and bright galaxies emerge so quickly? These puzzling findings have given scientists plenty of reason to reevaluate their long-held theories regarding the universe's evolution, because star formation is regulated by feedback mechanisms like supernova explosions. It was thought that galaxies that appear to have converted nearly all of their gas into stars could not be revealed by the JWST. Such data have the potential to completely upend the conventional lambda CDM cosmological model if they are confirmed. JWST has changed our view of the universe's origins and evolution in less than a year of scientific operations, suggesting that some of our most cherished beliefs may be incorrect in addition to pushing our cosmic horizon farther out. What if, however, looking farther into space also meant looking farther back in time than was previously thought possible? How much of the distant past can be seen in deep space? The fact that watching far-off objects is fundamentally a kind of time travel is among the most fascinating things about astronomy. Light from far-off stars and galaxies takes time to reach us because it moves at a finite speed of 299,792 kilometers per second. Astronomers can see light that left such objects billions of years ago when they gaze deep into space with powerful telescopes like the James Webb Space Telescope, or JWST. This gives us a clear glimpse of the distant past of the universe, since the farther we stare into space, the farther back in time we are witnessing. Astronomers are able to rebuild the cosmic history timeline thanks to this technique. Galaxies 10 billion light-years away, for instance, are visible to us as they were 10 billion years ago, long before Earth was born. Understanding the evolution of stars, galaxies, and other structures depends on the capacity to see several cosmic epochs. Scientists can now view galaxies as they were a few 100 million years after the Big Bang, during a time known as the Cosmic Dawn, when the first stars and galaxies started to glow, thanks to JWST's sophisticated infrared capabilities. It is known that the universe's expansion causes light from many galaxies that have been traveling for hundreds of millions of years to get stretched. Because JST could detect infrared light, it was believed to perform some sort of time travel magic. The light from many of these early galaxies was redshifted into the infrared, making it impossible for previous observatories like Hubble to capture. Astronomers may now study the origin and evolution of some of the earliest structures in the cosmos in unprecedented detail because to GST's equipment, particularly NIC-CAM and MIRI, which are built to capture this stretched light. JWST's image is a crucial record of the events that produced an early universe, not a glorified cosmic portrait. Scientists find that comparing galaxies from different eras is one of the most helpful ways to understand how matter began to shape itself, how star formation rates altered over time, and how cosmic architecture changed over billions of years. Deep space observation has a richer chronology of time than very few other scientific fields. The telescope is trying to find answers to some important issues regarding the universe's existence and our destiny by looking not only beyond enormous distances, but also back towards the beginning of all we know: galaxies that are too young to exist. The discovery of galaxies that seem to be significantly more massive, brilliant, and evolved than what conventional cosmological models predict for their age is among the most astounding findings made by the James Webb Space Telescope, or JDST. It is estimated that some of these galaxies, like GSZ 130 in Jade, were only 320 million years old when the Big Bang occurred. The commonly accepted Lambda CDM model states that galaxies were only starting to form around this time. However, systems that are already brilliant, star-rich, and structurally complex have been discovered by JWST. This maturity level appears to be unattainable in such a short cosmic time span. According to the traditional model of galaxy formation, gas cools, collapses, and forms stars over hundreds of millions of years, with feedback mechanisms like stellar radiation and supernova explosions controlling the rate of this process. Nevertheless, a few of galaxies observed by JWST seem to have rapidly converted almost all of their accessible gas into stars, eluding those typical regulating mechanisms. Long-held assumptions about how galaxies evolve are called into question by this unanticipated efficiency, which raises the possibility that early cosmic conditions permitted a formation process that was significantly faster or more aggressive than previously believed. Astronomers are currently looking into potential causes for this phenomenon. One theory is that the gas clouds in the early universe were significantly cooler and denser than previously believed. Gravity would therefore have caused them to collapse into stars more rapidly. An alternative theory is that some of these objects are actually active galactic nuclei, AGNS, or quasars, supermassive black holes that are located inside galaxies and emit intense amounts of light, rather than galaxies. This would mimic star-rich systems and reveal whether light is coming from accreting black holes or stars. The JWST's spectroscopic sensors will examine radiation patterns and chemical fingerprints. The ramifications will be historic as JWST continues to observe and confirm that these are, in fact, adult galaxies that formed within a few 100 million years of the Big Bang. This has the potential to fundamentally alter our understanding of star formation rates, galaxy formation, and, even more drastically, the universe's true age and expansion history. Some theorists have already proposed that the cosmos is either older than we now believe or that early structure building is accelerated by unidentified physical processes. Either way, the discovery of these unfathomable galaxies marks a turning point in cosmology and poses important queries regarding the early cosmos that we thought we understood well. Conflicting with the Big Bang chronology, the universe's evolution from a hot, dense origin 13.8 billion years ago to the formation of neutral atoms about 380,000 years later, and ultimately to the emergence of the first stars and galaxies hundreds of millions of years later, is outlined in the standard Big Bang model. Large, mature galaxies shouldn't emerge until at least 500 million to 1 billion years after the Big Bang, based on this paradigm. But just 300 to 400 million years after the universe's beginning, galaxies that appear completely formed and astonishingly huge have been discovered by the James Webb Space Telescope, or JWST, upending that predicted timescale. Our knowledge of cosmic evolution is directly challenged by these early galaxies. They exhibit characteristics including mass, structure, and brightness that are at odds with the current Lambda CDM model's predictions for galaxy growth rates. The fact that certain galaxies seem to have already used up all of their gas supply by forming stars suggests that star formation happened much more quickly than is predicted by current simulations. The idea that early star formation was sluggish and constrained by cooling times is refuted by this degree of efficiency. Response from gas availability and stellar winds. Because of this discrepancy between theory and evidence, some scientists continue to question whether the Big Bang timeframe is accurate. According to one theory, the universe is more than 13.8 billion years old, which gives these galaxies plenty of time to form. Other explanations suggest that either physics is still understood or that something else, such as the rapid cooling of gas in denser surroundings, accelerated the formation of galaxies in the early universe, or that incorrect interpretations of redshift data or dust-obscured AGN could change the estimations of age and distance, which could be an intervening factor away from the more widely accepted concept of early formation. Despite the fact that current spectroscopic research primarily supports the early formation theory, regardless of the reason, it is evident that the evidence suggests that our cosmological models may require significant revisions or remain unfinished. The rate of structure building and the conditions at the cosmic dawn are two basic assumptions about the early cosmos that scientists will need to reevaluate. With additional JWST observations, such inconsistencies between theory and reality could lead to a new and better understanding of the universe's early history, since huge, well-formed galaxies were spotting themselves shortly after the Big Bang. Is the cosmos older than previously believed? According to mainstream cosmological models and measurements of the cosmic microwave background, the universe is thought to be 13.8 billion years old. This estimate is based on data from missions such as the Planck satellite, which helped establish the structure and rate of expansion of the universe by mapping temperature variations in the cosmic microwave background. At very large red shifts, however, which correlate to a time when the universe was less than 400 million years old, galaxies that appear startlingly huge and mature have been discovered by new data from the James Webb Space Telescope, or JWST. There is a concerning prospect raised by these galaxies. The cosmos may be older than scientists believe, or our models of early galaxy formation may be lacking. With their mature structures, brilliant luminosities, and dense star populations, some of the galaxies found by JWST seem much too advanced for their age. Some even appear to have turned the majority of their gas into stars already, which is a behavior that is usually reserved for much later in the history of the universe. The cosmic timescale must be extended to account for the development of these galaxies if they indeed existed that early and are not misidentified things like active galactic nuclei, AGN. This has caused some astrophysicists to hypothesize that galaxies evolved much more quickly than previously thought, or that the present estimate of the universe's age may be underestimated due to a substantial unknown process. The persistent discrepancy between the expansion rates inferred from the measurements of the adjacent supernovae and the other set predicted from the early universe, CMBB data, is known as the contemporaneous Hubble tension. It is possible that early galaxies observed by JWST may have formed structure at a significantly higher rate than previously thought. This could challenge our understanding of expansion data or even imply that we need to complete a more intricate cosmic history. Some theorists even contend that the early inflation models need to be modified, or that we may be overlooking important details like the function of dark energy versus time. In any case, that would merit careful examination in order to make room for an older or differently evolving cosmos. However, given these fascinating ramifications, many renowned scientists urge caution. Other possibilities, like as gravitational lensing or observational bias, have not been completely ruled out because the redshift and age estimates of these early galaxies are currently being confirmed by spectroscopic investigation. The idea that the universe is older than 13.8 billion years must be seriously considered, though, if JWST discovers more distinct instances of fully formed galaxies at very far distances. At the very least, it supports the notion that the early cosmos was far more complex and active than previously thought. This challenges our understanding of the history of the cosmos. The surprises don't end there either. Inside those early galaxies, something even more surprising is taking place. Reconsidering the early universe's star creation, it has long been believed that the early universe's star formation was a rather slow process, limited by elements like cooling rates, gas supply, and feedback mechanisms from supernova explosions and stellar radiation. According to conventional wisdom, galaxies should only ever turn a small portion of their gas into stars, with the remainder being blasted out or cooked by intense events. This concept is beginning to change, though, thanks to observations made by the James Webb Space Telescope, or JWST. It appears that some of the early galaxies found by JWST have converted almost all of their accessible gas into stars at a startling rate, which is significantly faster than what is predicted by conventional models of galaxy evolution. The fundamental presumptions underlying current astrophysical simulations are called into question by this unexpected efficiency in star creation. These simulations, which simulate the evolution of galaxies spanning billions of years, usually incorporate feedback-based bounds that stop the production of runaway stars. However, a few 100 million years after the Big Bang, some of the early galaxies seen by JBST emerge as huge, luminous, and densely inhabited systems, defying those restrictions. These galaxies would suggest that early universe circumstances permitted significantly more efficient star formation than previously thought, provided they are real and not the result of observational errors. One explanation for this would be that the early universe's gas was hotter and more denser than previously thought, making it simpler for gravity to collapse hydrogen and helium clouds into stars. There wouldn't be much trouble. According to a different theory, those galaxies might have originated in a very compact way. They were able to hold on to gas and produce stars faster as a result. However, the advancement might have been impacted by additional invisible environmental elements, such as strong cosmic radiation fields or alternative cooling channels. Nevertheless, some of the objects found by JWST might not even be star-rich galaxies. Instead, they might be quasars, active galactic nuclei, or AGNs that imitate the light signatures of stellar populations. To distinguish such situations from one another, JWST follow-up spectroscopy is essential. Astronomers will be able to determine if the light is indeed coming from stars or from matter whirling around a super-large black hole by examining the elements and emission lines seen from those galaxies. And substantial revision of the forms in which galaxies formed in the very early phases of the universe will be challenged if JWST continues to confirm that the majority of these ancient objects do, in fact, belong to their stars. These could rethink the physical conditions of the cosmic dawn, the principles governing star formation, and the roles of the dark matter scaffolding. The strain in the Hubble. One of the most important unsolved issues in contemporary cosmology is the Hubble tension. It alludes to the enduring disparity between two approaches to determining the Hubble constant, HU, which stands for the present rate of expansion of the universe. An estimated lower value of roughly 67 to 69 kilometers per second per megaparsec is suggested by measurements based on the cosmic microwave background, specifically from the Planck satellite. However, a much higher value of about 73 to 75 kilometers per second per megaparsec is obtained from direct studies of nearby supernovae and Coffee variable stars conducted by scientists like Nobel laureate Adam Ree. The fact that the difference between these figures has not decreased, despite increased accuracy on both sides, raises the possibility of a more serious problem. This conflict is not insignificant. It suggests that we might not fully comprehend the early cosmos or basic physics. This mystery has been further complicated by the discovery of galaxies that appear more advanced and structured earlier in cosmic history than previously thought, according to the James Webb Space Telescope, JWST. The assumptions that underlie measurements of expansion and distance may be impacted by these discoveries. For instance, our interpretation of light from far-off sources may change if galaxy formation happened more quickly than previously believed, which could have an indirect impact on computations of the Hubble constant. According to some scientists, the Hubble tension might point to novel physics that is not covered by the conventional lambda CDM cosmological model, which also contains cold dark matter CDM and dark energy lambda, time-varying dark energy, changes to gravity, or the existence of new particles that would have changed the universe's expansion pace at some point soon after the Big Bang are some of the potential explanations put forth. Others propose that skewed results are caused by systematic measuring errors. However, the likelihood that the phenomenon is real and not a fabrication keeps growing as each technique is improved, but the tension still exists. New missions like NASA's Nancy Grace Roman Space Telescope and ESA's Euclid satellite will launch into space to offer more precise measurements of astronomical distances and expansion across a far greater region of sky, therefore resolving the Hubble tension. In the meantime, JWST's early observations provide an alternative perspective on the early cosmos that could be crucial in demonstrating how early galaxy formation differs from CMBB theories. The Hubble tension is an uncommon occurrence in research, regardless of whether it results in new physics or enhances existing models. A reproducible, well-characterized oddity that has the potential to fundamentally alter our view of the cosmos. Dark energy and dark matter, the fundamental elements of the conventional cosmological model, are dark matter and dark energy. They are still, nevertheless, one of the most enigmatic physics aspects. The cosmos is made up of roughly 68% dark energy, 27% dark matter, and only 5% conventional baryonic matter, according to the lambda CDM model. Despite having insufficient visible matter to explain their gravitational attraction, galaxies and clusters are able to retain their structure because to dark matter. In contrast, measurements of distant type Ia supernovae in the late 1990s revealed that dark energy is the hypothesized force responsible for the universe's accelerating expansion, work that won Nobel Prizes for scientists like Adam Ree. Dark matter and dark energy have never been directly observed, although playing crucial roles in the paradigm. It is hypothesized that they exist because to the influence of cosmic expansion and gravitational processes. The reliability of the current knowledge of these components is being called into doubt by new findings from the James Webb Space Telescope, or JWST. Massive galaxies with very large red shifts that appear to have formed just a few hundred million years after the Big Bang have been discovered by JWST. Assuming gradual dark matter scaffolding structures throughout the universe, such galaxies seem far too big and advanced for the period available today. The question of whether dark matter acted differently in the early cosmos than it does now has been raised by this congruence. Other types of dark matter that might cluster more quickly or inconsistently with cold dark matter are being considered by some physicists. Dark matter that is warm or self-interacting, for instance, is suggested. On the other hand, others invoke a different resurgence of dark energy pathways over time. A different pace of structure formation would have been induced to support the JWST data without totally rejecting the standard model if dark energy had behaved differently in the early universe than it does now. Though they typically struggle to explain many data at once, modified gravity theories have also been proposed as alternatives to dark matter and dark energy. The need to better understand these dark components is highlighted by the discrepancy between JWST observations and existing cosmological models. Even if the CDM still explains a large portion of what we observe, including the cosmic microwave background and galaxy distributions, oddities like these early big galaxies force scientists to question their long-held assumptions. Therefore, the questions raised by JWST suggest that we may still be surprised by the dark sector, surprises that we could attribute to the discovery of new particles, changes to the laws of physics, or the gradual taming of dark energy and dark matter. Background of cosmic microwaves. The oldest light in the universe that humans can see is called the cosmic microwave background, or CMB, a remnant from around 380,000 years following the Big Bang. For the first time, photons could move freely because the cosmos had cooled enough for protons and electrons to combine to form neutral atoms. The CMB is made up of these photons that have been stretched into microwave wavelengths over billions of years of cosmic expansion. Tiny temperature variations in the cosmic microwave background, which reflect the density changes that ultimately resulted in the development of galaxies and large-scale cosmic structures, have been traced by observations from satellites such as WU-MAP and Planck. The conventional cosmological model has been significantly influenced by the CMBB. It offers accurate measurements of important characteristics at early times, including the density of matter, the density of baryons, and the expansion rate of the cosmos. Additionally, it lends credence to the idea of inflation, which explains why the CMB appears almost the same in all directions, a property known as large-scale isotropy, and the universe's quick expansion in the initial fraction of a second. Scientists are now wondering if there is physics beyond the present model, or perhaps evidence of a multiverse, where collisions between cosmic bubbles could leave imprints in the CMB in light of some small anomalies in the CMBB, such as the so-called cool spot. The Webb is an excellent complementary tool, even though it is not designed for direct CMB probing. Watch Hubble here as it looks at galaxies that were formed only a few hundred million years after the Big Bang, allowing astronomers to compare the structures that emerged in the early cosmos with those that the CMB anticipated. It may be necessary to alter important assumptions about the universe's development if there is a significant departure from CMB-based models in the distribution size or creation rate of galaxies at high redshift. In a single view of cosmic history, this links the first stars and galaxies to the very first light of the universe. Scientists are keen to see if any new features of the universe's primordial structure found by JWST match theories based on CMB data, or if there are any more recent differences. Any such persistent discrepancies between JWST observations and CMBB predictions may suggest that we are missing some information about the early cosmos, maybe related to starting circumstances, inflationary processes, or dark matter interactions. Together, JWST and CMB investigations are completing a more complete and maybe more complex picture of the universe's beginnings by connecting the CMB era with the cosmic dawn. A more profound query emerges as we relate the light of the ancient world to the truths of the present. Is a new theory of the cosmos emerging? Many scientists are starting to doubt whether the mainstream cosmological model known as lambda CDM can continue to explain the universe in its totality in light of growing evidence from the James Webb Space Telescope, or JWST, that shows irregularities in early galaxy formation. This model has long been the foundation of contemporary cosmology and comprises dark energy, lambda, cold dark matter, CDM, and the Big Bang, followed by cosmic inflation framework. However, this paradigm has been under criticism when JWST discovered huge mature galaxies that existed only 300 to 400 million years after the Big Bang, indicating that some essential elements of our knowledge may be lacking. The possible necessity to update or alter portions of the Big Bang timeline is among the most important ramifications of JST's data. Assumptions regarding the rate at which stars and structures can develop under present physics are called into question by the existence of galaxies that seem to have evolved for their age. Researchers are looking into the possibility that these discoveries are the result of inaccurate mass or distance estimations, but if verified, they would suggest that galaxy formation started sooner or moved more quickly than our models predict. This has prompted theorists to investigate alternate universe models, such as those that include novel physics not found in the conventional image, or those that incorporate earlier or more efficient structure generation. Models based on quantum gravity, cyclical worlds, or variants of cosmic inflation are some of the more extreme theories that are gaining popularity. According to some theories, the cosmos either endured numerous expansions and contractions or emerged from a previous condition before the Great Bang. Others use concepts like modified gravity or a different speed of light to explain differences. Nobel laureates like David Gruss and Adam Ree have highlighted that scientific crises, like the ones that are currently occurring, frequently lead to innovations that bring together more ancient theories with fresh perspectives, particularly when it comes to bridging the gap between quantum mechanics and cosmic scale physics. Unresolved evidence from early galaxies to the now dominant Hubble tension indicate that cosmology is going through a turning point, even though none of these new theories have yet to overthrow the conventional one. Future missions like NASA's Nancy Grace Roman Space Telescope and ESA's Euclid will gather information to confirm these discrepancies or refine existing ideas. In any case, it appears that we are at the beginning of a new era in our understanding of the cosmos that will fundamentally alter our conceptions of time, space, and the genesis of all things. Furthermore, the emergent theory of gravity and modified gravitation theories like MD or modified Newtonian dynamics are being studied to explain the observed occurrences. Even though these have frequently been categorized as parental beliefs, they are given new vitality by just observations. According to Dr. Priyam Vadanatarajan, a Yale astrophysicist with a theoretical bent, we are witnessing a breakdown in the typical behavior of structure building at the earliest epochs. Even if it involves rethinking the very forces we believe to be essential, that calls for bold thinking. In the meantime, philosophers of science and cultural scholars have started drawing parallels between the event and other scientific revolutions, such as the transition from Newtonian physics to Einsteinian relativity. This serves as a reminder that science advances not only by providing answers, but also by challenging the assumptions we take for granted. Thank you for viewing. Please remember to like the video, subscribe for more incredible space discoveries, and leave a comment below if you were as enthralled as we were. Thank you for watching the video. Please like and subscribe for similar content.